Hi everybody, in this video we're going to be looking at mass spectrometry and in particular we're going to look at fragmentation. Now this video is aimed at A2 chemistry students, so there is a requirement for you to know some mass spectrometry already to be able to understand this, and that is from AS chemistry. Now I've made a list of some of the ideas that you should really know from AS chemistry, and this is how a mass spectrometer works, how to read a spectrum as well, and also identifying elements and isotopes as well. So if you're not sure on how to do some of them basic mass spectrometry tasks, then there are videos that are linked for this. So if you just look at my AS chemistry playlist, and if you just do a search for mass spectrometry, you can find some videos on there first. But for the purposes of this, I'm going to assume that you know some basic mass spectrometry already. Now, at AS Chemistry, like I say, all you expected to do was to be able to look at a mass spectrometer, a mass spectrum, and be able to identify specific elements in there by using the spectrum that you've been given. And hence, you'll be able to calculate as well relative atomic masses of an element based on the isotopes that you get from a mass spectrometer. That's fine, but A2, they expect you to take that one step further, and they expect you to be able to identify molecules instead of just atoms. So we're taking it a little bit more complex step. And that's effectively what we're going to look at here. And we're going to look at this kind of idea of fragmentation as well in a mass spectrometer. So just to remind ourselves about how a mass spectrometer works. Basically, a mass spectrometer is obviously something which can help to identify, it doesn't always identify because there's a lot of molecules with similar masses, but it can go towards a set of analytical techniques to identify an element, but effectively it's used to identify a sample. Now, what you do is you inject your sample into your mass spectrometer. Normally it's through a syringe or you generally inject it into your machine. Your machine has a built-in oven that can heat up and it can vaporize your liquid sample into a gas. And it's really important because mass spectrometers only work with gaseous samples, so they must be vaporized already if it's not already vaporized. Once it's been vaporized, the next step is actually it's been ionized using a high energy electron gun. And what this does is it knocks off an electron from your atom and it creates a positive charge or positively charged ion. Now, you need positively charged ions for them to be able to be accelerated through a set of negatively charged plates. Anything that is not positively charged will not go through your mass spectrometer, and this will be important when we come on to this as well in a minute. Once it's been accelerated, it's then deflected using electromagnets and then is detected on an electronic plate at the end. And we can obviously detect our different ions that have come through and obviously measure the mass of them. That's what a mass spectrometer is. So we're going to apply this to a molecule, and there's a little phrase that I want you to try and remember here, and that's be positive about radicals. And the words which I've emphasised there are positive and radicals, and I'll come on to that in 2 seconds just to say what that means. Okay, so unlike atoms, like I say, molecules can be broken up. So atoms obviously just exist as one atom and they cannot be broken up. So when they go into a mass spectrometer, all that you get is the different types of isotopes that are distinguished. But the moment you put a molecule in there, that molecule is effectively broken into little fragments or little bits. And we call this fragmentation. And this is the phenomenon that I'm going to explain here. Now, when you take your molecule, I've got this one here, which is propanol, propan-1-ol. Now, if I inject propan-1-ol into there, propan-1-ol is a liquid, that's vaporized into a gas first, and then it's ionized. And it's at this point when it's ionized that actually your molecule starts to break up into different bits. Now, what we're going to do is we're going to split this into different parts. Now, it'll break at strategic points, mainly, obviously, weaker bonds of the molecule. And the weakest points are actually between your carbon-hydrogen kind of chunks. So you can see here we've got a CH3 bit, and I've separated that with a green line. So our mass spectrometer can split the molecule there into two different parts. It can also split it here, and it can also split it at this point here as well. And sometimes it might not even break the molecule up at all. Sometimes the whole molecule goes through the mass spectrometer as well. And effectively, this is called fragmenting. We're breaking up the molecule. So we're going to see what fragments we can get and what influence that has on our mass spectrum down here as well. Okay, so we're going to look at the first one. So if we fragment at step 1, so I'll put that over there. This is step number 1. Effectively, what we can make are 2 different possible positively charged ions. So we can form this, which is CH3, and we could have a positive charge on that. And if you look at the rest of the fragment, which is this here, you could also form CH2, CH2, OH. Now that's got to be a radical. Now effectively, this is where this phrase comes in. When you fragment any part of a molecule, you must always form a positively charged ion and a radical. You've got to form a positive and a radical. So if one side is a positive, the rest of the molecule has got to be a radical. Now obviously this could be the other way around as well. So I'm just going to put OR there, and effectively this could also be CH3 dots, and then you can have CH2, CH2OH as your positive charge. So you could get either or. But you can see here that the positive charge, this one and this one, these are the only 2 fragments which will actually get pulled through your mass spectrometer. These radicals will not exist. They will not actually go through your mass spectrometer because they don't have a positive charge. So these are the 2 fragments, our first 2 fragments, which could go through our machine. Now, if we look at the next step, this one here, so again, if we be positive about radicals, when you fragment your molecule at this point, it could fragment there. Again, it's a reasonably random process. So this is the potential fragmentation point. You could form CH3, CH2, positive, or you could form on the other side, which is CH2, so the rest of the molecule, OH, and that could be a radical. Or you could form the opposite. So this one could be the radical and this one could be a positive charge. So we'll write that down on there. So you can form CH3, CH2, radical, or you could form CH2, CH2, OH, and that could have a positive charge. But again, the only ones which are going through here are your positive charges. And finally, if we break our molecule there, which is on the blue dotted line, so I'll put that as, I'll call that one 3, I'll call that red one 2, just so we're making it really clear what's happening. So if we break it there, then obviously we can have the left-hand side, so this is number 3. So what we can form is effectively to the left, we can have CH3, CH2, CH2, and that could be a positive charge, and then you would have an OH as your radical, or you could have CH3, CH2, CH2, and that would be a radical, or this could be the positive charge, so that could be OH plus. Now you can see here that, I'll just rub that out. You can see here that we could have either this fragment or this fragment here. Now, you can see that we've also got radicals. Now, the radicals, remember, don't go through your mass spectrometer. So the only bits that we're actually interested in, and I'll do these in purple, are actually our positive ions. So our positive ions in total are these ones. So we can have that going through our mass spectrometer. We can have that. We can have that going through our mass spectrometer. This fragment, and this fragment. So the ones which I've identified in purple are the fragments which would actually go through our mass spectrometer. Now, if we were to detect these, we would actually find that obviously these have a different MR, and these are the only bits which would go through. The radicals actually won't go through at all. There is one other bit as well, because I did say right at the start that actually you might not get any of this molecule fragmented. Sometimes the whole molecule goes through, the ionized version of the molecule, so you might get this fragment as well. So you could get this one, which is CH3, CH2, CH2, OH, and that can have a positive charge. Obviously, it has to have a positive charge for it to go through your mass spectrometer. This is what we call the molecular ion, because this is the molecule that hasn't been fragmented and it's the full mass. So this would be the peak that you would see on the far right-hand side of your mass spectra as well. But you would also see these bits on your mass spectra. You'd see fragments of these. Now, these have a different mass. So, for example, CH3 plus has a mass of 15. So you'll see a peak at MZ15 because it has a CH3 charge. You would also see a peak at 17, and that would tell you have an OH plus charge as well. So you can see you've got all these different fragments here that would make up your spectra, plus any molecular ion that you might achieve as well. But that's it. There are videos that look into how we can look at the mass spectra of molecular ions like this. But other than that, that's it. That's all we need for fragmentation. But I hope that helps. Bye.